write this in the formula, but you have this so you have this square. This is just easy. So I think it's just somehow. Well, maybe we
well, you see that we don't that's
it's a one. But then you have to make this more precise.
So this is 4 times 12. This is air. So you divide by this. So rho x is the line of 4. Dynamics is a length. No. So if you not one.
The each of them is
Square.
each pair of them.
Yes, so if it's determined by those squares, so you just construct. Yeah, it's not
Usually this is denoted by
With the chair. Maybe still 1 more minute. You look at the clock, it's not exactly right.
because Tima left. I see. What is it?
New chair.
Yes. Local. Very local. So the next talk by Louis Funar about topological quantum field theory.
Thank you. Okay, so should resume on the point I left yesterday. What is a TQT? As I said, a functor from the category of coordinates in dimension 2 into the category of vector spaces over C. One important point is that vector spaces should be finitely dimensional. Okay, so the axioms in better shape than yesterday. First, this is functorial. That means if you have M1 with and here you have M2, here you have the boundary of M1 is split into two pieces, two disjoint pieces, and here is the same. Then you have 0, M1 composed M2 equals 0, M1 composed Z M2, where Z is a function. Okay, in order to make this precise, you have to add the condition that the boundary, each boundary component, so each boundary component of D plus minus M is marked. The markings are exactly like we talked by Hugo. Mainly you have, for instance, a homeomorphism on some standard fixed surface of genus G. For some G from 0, 1 to infinity. And this marking is considered up to isotopy. Okay, on the left side. The second is the second action is what I call the quantum action. Is when you look at the vector spaces associated to surfaces, if you have connected several connected components, then you have this translates into tensor product. Usually I'm calling Z of sigma G W G, just making notation a bit simpler. And as I said, you have two additional conditions. Empty set is C, and also traditionally you consider Z of the two spheres is also C. That's called reduced TQFT. Just to make things a bit simpler. So there are a number of remarks. What we'd like to achieve in general in this theory is to obtain spaces WG finite dimension. This is a key point in the construction because it's not that difficult. I'm going to show you immediately how to construct infinite dimensional, and there are even some universal ones.
So in condition 1, what is the ZM1 dot ZM2 dot?
This is a composition of morphic because the morphic have every boundary marked. The composition is
composition.
Composition
On the right hand side, what is that?
And this is the composition of morphic.
Composition morphism.
So Z, well, if I have two components, sigma 1 and sigma 2, then Z is Z of M is a map from Z of sigma 1 into Z of sigma 2. And some vector space is morphic. Now, the second remark is a warning that in general you need additional structures to respect to what I defined here. These additional structures are called P1 framing or P1 structures or planes or whatever on surfaces and also on free manifolds and cohomologies in order to construct non-trivial. Namely, instead of having this natural relation up here, you generally get something like z of m1 is equals to some theta time, where theta, let's say, is u1. This is what you get in reality. This is not just an artifact of there are some deep reasons to obtain that, and there are very nice applications to the structure of central extension of mapping class group because of this additional structure, which makes a big difference with respect to the simplicity. Maybe at the end of the second talk, Friday, I can say a particular example concerning the residual finiteness of central extension. Okay, so let me say a few more words, more particular such cohomologies. Namely, I'm taking here the surface sigma g, the cylinder around the surface, so it's sigma g cross 0, 1. But now you have two boundary components, and I need two markings. One marking is just identity, okay? And the second marking is some diffeomorphic phi with the same surface sigma g. So what we get here is traditional called the mapping cylinder of phi. So it's topologically trivial. There is no non-trivial topology. Nevertheless, this theory should give you something. So it's a kind of first exercise. The map which associates to rho 2 to phi, which is an element of this homomorphic group of sigma g. Z of m phi, which is an endomorphic of the vector space I call WG. Factor a factor through the mapping class group, which is the diffeomorphic group of sigma g divided by the connected component of the diffeomorphic group. And now, just to make things coherent with what I wanted to have only theories related to connected components, I'm putting some plus here, meaning they are preserving the orientation. One extra plus here that is not important. So this is the mapping class group in GSG. And the exercise is to show that this is a representation of the mapping class group. So this is a representation. I'm calling this representation, let's say, rho of course depends on G, but also depends strongly on the choice of the community. So this is one of the main characters. Now, you know that free manifold and free has a natural decomposition called Hagar decomposition into two handle bodies. So I'm calling one Hg plus, the other one Hg minus. So handle body means exactly what the surface an anknoted surface into the sphere, it bounds on both sides. So this is interior up here, it's HG. They have two copies which are glued together by identifying their boundary. HG plus is identified with the boundary of HG minus by means of some homeomorphism of diffeomorphic phi. And now of course you can do that in many ways. Nevertheless, the functoriality is giving you a very simple way, say, to catch the invariant of M3 by using just the vectors and covectors determined by AG plus. So AG has one boundary component, but you could always add the empty surface. So you could consider it on one side as a coordinate from the sigma g to the empty set, and the other side from the empty set to the sigma g. So if you look at the coordinates from the empty set to sigma g, then z of hg can be seen as a map from C to sigma g. That means it's a vector, let's say call it small wg, is a vector of the space wg. It's just abstract nonsense what I'm saying here. But on the other hand, you could have z of hg, I'm just putting here plus and minus, also as a map from wg to empty set, so it's also a functional. Let's say it belongs to wj star. It's the dual of wj. So z of m3 then could be read in a wj star composed by rho of phi. Actually I said phi, but it's only the class of phi in the mapping class group which really matters here, composed with wj, or if I'm saying composed, you could put also of wj. So this is the expression of z of m3 viewed as a coordinate from the empty set to the empty set. So this is a number. So actually you really give a number. Here this is a functional, this is a vector, you take the representation of the vector and you get that. So this is a number of C. So that's the way you get an invariant out of all this. So now vice versa. The two ingredients I put here, so this is, let's say, exercise 2, but it's almost trivial. Given the data of the mapping class group representation plus some vectors like that and covectors, then you could retrieve not only closed free manifold invariants, but you could retrieve the TQT completely. This is not much more complicated, but let me say maybe just 2 words about. Yeah, there is some additional technical condition. Right, I think called it non-degenerate TQFT. Let's say you take Wj. So Wj is Z of sigma j, and you have a lot of free manifolds bounding sigma g. So you have a lot of vectors here. Z of m is a vector in Z of sigma j for any m with boundary of m homeomorphic to sigma j. any free manifold giving you a vector there. So the non-degeneracy condition, or the TQT called non-degenerate, and we always we use this kind of non-degeneracy. Gonna see in a minute why. If well, the span of Z of M over all M, which are free manifolds like that, is precisely the whole sigma j. So in some sense, the theory is really meaningful for free manifolds if the vectors obtained from free manifolds are spanning all of that space. And now this is permitting us to define a very, well, a bilinear, but if you have extra structure, let's say that if your invariant for free manifold has the property that changing the orientation, it conjugates the invariant and things like that, you can go to a sesquilinear form and sometimes to a Hermitian form. But for the moment, just to keep things simple, you have a bilinear form, B with the property of Bxy is basically y star of x, where x and y belongs to Wj, and this is only defined in terms of invariant of closed free manifolds if you look carefully. Okay, because x and y are linear combinations of vectors associated to free manifolds, and then that means that you will always have some manifold on the left coupled to some other manifold on the right, and you do things like that only using free manifold. Okay. Now the next step is to see that there exists. So for the moment, what I said is not so deep as it might seem at first glance, because there exists, let's say, a universal TQT. This universal TQT is kind of tautological, but it permits to make a construction that transforms every free manifold invariant into a TQT. So this is much more interesting, because you can think also to, let's say, you take an invariant like the homology, and out of the homology you can construct some representations of mapping class groups. They would be, of course, not very interesting. But there is something already. The universal TQT, you have a vector space W around Wj, which is the C vector space Q, which is infinite dimensional. Well, if you just take all M, which are free manifolds, such that you have also an identification with sigma j. So you take M all free manifolds. You could take them all connected or whatever. There are a lot of variants of such things. And this is a marking on the bound. This is a huge infinite dimensional space. Nevertheless, you have also a bilinear form, which is very similar to this B out here. The bilinear form from Wj in around is not taking values in it is not taking values in C. It's taking values in something else. Well, I'm putting a question mark in that. The idea is that B of the class of M here and the class of M here is nothing else than well, is a free manifold now. Is a M union N. what would be interesting? Well, let me tell you that there are some deep questions concerning this universal TQFT, because you get automatically a representation of the mapping class group, which is just the one twisting your marking. Then you have this form B, which is a bilinear form which is giving you a duality, and you could take the vector Wj being exactly the vector corresponding to the handle body. So you get kind of TQFT. You can put here some ring, well, let's say some group on the set, the group generated by all closed free manifold. Okay, so you can take a linear combination of such free manifolds. This is the, well, we put a kind of extra structure on it. So you actually could retrieve a full TQFT. I would say more just when I make an additional supposition. And it's a deep theorem of Friedman, Walker, and Caligari, Friedman, Walker, saying this universal TQFT is a positive definite pairing for free manifold. So this is a positive definite in some sense, meaning that it's a non-degeneracy of this bilinear form. This is not anymore true in higher dimensions. At least 5, I'm sure, probably also on the dimension of this 4, is not anymore true. So what is the meaning of that? The meaning is that in some sense, TQFT, if you accept infinite dimensionals also, but they are very close to classified free manifolds. So on the other hand, going to higher dimensions, starting with dimension 4, TQFT defined in this precise way and complete analogy will not be able to find, let's say, exotic 4 spheres or whatever, or diffeomorphic. There will be always examples of 4 manifolds which are diffeomorphic and non-diffeomorphic and not able to be distinguished by any from such invariants. So there is need for additional structure, additional non-trivial structure to catch this kind of high-dimensional phenomena. So now I'm doing something very, very simple. Let's say that in addition to all this, you have an invariant defined for free manifold. A numerical invariant for closed free manifold. So that means that here the group generated by all free manifolds could be replaced by C. Because if this invariant, I call it I, just to make it different from Z, to add more entropy. So here I can put I. So, of course, this bilinear form would be quite huge now, and it would have big kernel. So then the way to change something would be to define small wj, or not small, but script w, script the usual Wj, is just the quotient of the script Wj from before, find by the kernel of the form B1. The advantage would be to get a non-degenerate form, bilinear form, on a vector space which has now chances to be even finite dimensional if you choose carefully the invariant I. And additionally, what you get is a representation of the mapping class group inside Wj, which so the representation we use is from Mg now into, I would say, the unitary group. It is not a real unitary group because nobody says that this bilinear form induced on Wj is positive definite. Nevertheless, it is pseudo-unitary in some sense. So it is preserved. So the unitary with respect to the form B. So the form B is what is the restriction of B to Wj. So this is the so-called canonical extension of, I'm putting here, what is in green is the canonical extension of free manifold invariant to a TQFT. Okay.
So the invariant classify your TQFT? Your invariant is closed manifold?
The invariant has an invariant defined for closed free manifold has a canonical extension to all coordinates. This is what I'm saying.
Okay, but not every TQFT arises from.
Well, there are TQFT which does not arise this way. But in some sense, in some sense, probably they are not essential to the classification of free manifolds. You take a TQFT is giving you a free manifold invariant, and you construct another TQFT, which is slightly different, but not precisely the same, but essentially the topological information should be the same, more or less. Okay, so what is the data you can get out of this stuff? I'm putting it here like a small proposition, an easy proposition, lemma, whatever. So what is a TQFT in this sense? It is the data formed by a family of representation of mapping class group Wj, some vector space is Wj, of course, representation in a vector space. You have some specifics, vectors Wj belonging to Wj, and also some bilinear forms Bj, which are not degenerate. And now you need some additional condition. You need that rho G of some subgroup Mg plus, I'm going to say in a minute what it is, keeps invariant Wj. Mg plus is the image in the mapping class group of those diffeomorphisms, which of so the image classes of phi, where phi is a diffeomorphism of sigma j, which extends to the Hamel body Hg. Is a group considered first by Suzuki, if I remember, the subgroup of the mapping class group, also called the Handel body group, because it is actually the Handel body group of the diffeotopy group of Hg, the mapping class group of Hg. Okay. And the second condition is that you have a number of, this is something which seems a little bit complicated because not canonical. So you have the mapping class group of genus G surfaces with one boundary component, I'm putting it up here, which of course leads project on top the mapping class group. Then you have the mapping class group of some other surface. Now you have here M H, here J and H are arbitrary, and now you have a natural extra map, the gluing map. So this is the gluing map of surfaces. So surfaces, as soon as you have boundaries, can be glued together. And as this gives you a map into M, G plus H. And there is something else here, but it is not a group homomorphism. And of course, there is a theorem saying that it cannot be a group of homomorphism, but there is a map. The idea is that starting from X and Y here, you can construct a number of images here, infinitely many. I'm calling that connected sum. And as I said, there are infinitely many. And you need some identification of Wj also Wh inside Wj plus H, such that, well, the bilinear forms I'm going to write them in the bracket notation or the unit product notation. And I'm forgetting J plus H. The idea is that X connects sum with Y when you take the representation should act on this subspace. So if you take X, Y, E, Z tensor T, exactly as each component individually. Draw X. So put A, B, C, D for the vectors. So this is kind of compatibility of representation among data. The proposition is that this data is the same thing as a TQFT. It is a TQFT, let's say, the canonical extension of free manifold invariant. From where comes this kind of relation here? Well, it's just an avatar of the Reidemeister-Zinger theorem, saying that two handle-body two Hegar decompositions of the same manifold are obtained one from the other by looking at the free manifold M3 as obtained from itself by adding a sphere, making a connect sum of a sphere. So here is a small disk and here is a sphere S3. This corresponds to the Hegar splitting to adding one handle, which is a handle coming from S3 and its complementary, which is a natural identification along this handle line. And this kind of theorem is saying that because a free manifold is two such Hegar decomposition are obtained one from the other using this kind of stabilization. So in order to understand better such objects, for the moment they seem rather complicated. Why such things are complicated? It's just because we don't know so much about mapping class group representation, and we don't have to have only one. You need to have mapping class group representation in every genus. There were results by Lubotsky, Farb, and Margalit. Let's say first Farb, Lubotsky, Minsky, saying that if you take a representation of mapping class group into something like GLG, any representation of this a finite image.
Could you describe the level?
Sorry? You don't know all this? Should take a master class. So any representation like that has a finite image. So actually what he's saying is that this representation couldn't be that trivial. So this kind of result has been since then, this is about 2000. It was completely superseded. For instance, there is a very nice result by Franz and Handel on one side independently, and then by Horkheimer. Saying that representation from the mapping class group into GL and C for n smaller than 2g minus 1 have always finite image. Yeah, it's very close to, I said here. So they proved something weaker, sorry, but nevertheless it is true. So for n smaller than 2g minus 1, any representation has finite image. But on the other hand, if you go into dimension 2g, there is only one representation, namely it factors to the symplectic group 2g minus z, which is embedded up here. And the map from the mapping class group into the symplectic group is the map which take any phi of mapping class group, and you look at its action phi star as an automorphism of the H1 of the surface with its symplectic form omega. You can see that, yeah. The fact that this map is surjective is an old thing due to Burckhardt in 1890s. And this is very amazing in the, this is the case of orientable surfaces. For non-orientable surfaces, nobody cares about this kind of map up here. And this was proved, somebody proved it Gadget with somebody else, just in 2000, that there is an analog in the non-orientable case. The same. It's slightly more complicated. This is a non-trivial statement. Yeah. Okay, so if you want to construct by hand such representation of mapping class group, you won't succeed without without extra tools. Okay, so let me say things about the mapping class group or their presentations. So this is mapping class groups and presentations. Yeah. So if somebody really wants to see why mapping class group are interested, why people interested in mapping class group should care about TQFT, let me give you some points. There are a lot of people not from the master class here, and this bothers me because I only say the trivial things in, for specialists. Let me also put some theorem. I'm not sure. I could explain a bit at the end of the master class if we have time. One of idea of using mapping class group is that mapping class group they have some arithmetic counterpart, namely the profinite mapping class group. So this profinite mapping class group is the profinite completion of the mapping class group. The mapping class group is a residually finite group. MG is a residually finite. It is known since the 60s. There is a very nice proof using Teichmüller theory by Ivanov. And yeah, the residually finite means that any A in a mapping class group which is not 1 can be detected. There exists some map phi from the mapping class group into a finite group F, finite, with phi of A different from 1. So this is a known thing, and because of that, a more fancy way to say that is that the mapping class group is contained into its mapping class group into its profinite completion. So the profinite completion is by definition is the limit of mg divided by k, where k is a finite index in mg. So is a projective limit of finite quotient. So this is a topological group. So now, how big is such a group? So for any n, for any k, there exists n, well, let's say nk going to infinity, and also bigger than k, let's say like that, such that the profinite completion, but also the mapping class group itself is projecting surjectively onto the product of SL. Now I'm taking n, and I'm taking here something now Z of L is the itself kind of profinite group. It is the Eladi completion of Z. That means, let's say L is prime, then is a periodic integer. So you have such copies, k copies. Okay. So this, what is saying that this is huge. Okay, and not only it is huge, but this n can be arbitrarily large, but g is fixed. Okay, and you have several such copies. So this is something, let's say, non-trivial. completely different from what you can expect from the symplectic group. So this
So the product varies. So what is this K?
okay, so you take a product, or let's say some K times. K times. The product of K times of
varies
SLM.
along the it's L is like okay.
Okay. So here S has that. Okay, so
For example.
So for any L,
L, who is L? Then?
yeah, who is that? Take L.
Or is it the product along all primes?
Bigger than some L0 of
7 is not good.
you can take L equals 7, 4. Yeah, you can take L equals 7, but then N. No. I prefer to write it like that. L bigger than L0 of GFN, and that's clear. Okay, so you should take L big enough. If you fix N, you should have L big enough.
Why this K? K equal to 1 is already strong enough.
Yeah, but this is even more amazing because you have a product. Surjecting onto a product is not easy. If surject for K equals 1, this does not imply it's surject over K equals 2. If you try to do the same thing with the symplectic group, then N should be always bounded by 2G.
so this implies the profinite completion is not finitely generated.
Right.
Oh, I see. This is huge. Yeah.
It's really huge. Of course, for free groups, you can get the same phenomenon. But the mapping class is far from being free. This is the main interest.
So is there any comparison of this group with the Cremona group or something? I just heard about the Cremona group is also very big. In this.
I don't know. We can take talk later. Yeah. This is just for having something to look at. Because the other thing I'm gonna tell you is are really elementary on the mapping classes. So it's kind of motivation, ultimate goal of the series of lectures. So elements of mapping class group are studied exactly as we will start with this series of lectures by looking at its action on curves. And curves are considered always because of isotopy. You maybe are aware since a long time, but let me state it explicitly. This start point of the theory, the Bayer-Epstein. Sorry, it's Epstein or Epstein, because my colleague Greg is always saying Epstein. It's a subtlety. So embeddings of S1 into sigma j, which are homotopic to identity, are actually isotopic. And this is true if G not equal to 0. This is not true when G equals to 0 because there is when just a small difference is the orientation. Yeah. So and this isotopy is of course endless. So what is the immediate corollary is that if you have H defined from a surface and two with boundary. So this is a diffeomorphism or homeomorphism, which is homotopic to identity. Then it is isotopic to identity. This is of course true, as a side remark, true for M equals S free. This is a so-called surf theorem. But this is not anymore true in higher dimension. Not true for S7 and so on. Okay. So let me make some more remarks of the same kind. The group of diffeomorphisms which are isotopic to identity is a huge group, is a connected component of them because of this Bayer-Epstein theorem. It's exactly the connected component of identity inside the group of all diffeomorphisms of sigma j. This group is very interesting. It is huge, of course, but it is algebraically simple. So from algebraic viewpoint, studying diffeomorphism group of sigma j or the mapping class group is basically the same thing for many applications you can have in and this is true also for the homeomorphic group of sigma j, and for other homeomorphic group of manifolds, but in the case of diffeomorphism going into higher dimension, it completely changes. You have to take, they are not non-trivial. They are not anymore simple. They are homomorphism into R and so on. Okay, so if you take, there is a old and known proposition due to Magnus saying that if we have a free group, now FR is the free group with R generators, and you, well, N, and you have two elements, so this is free group, and you have two elements which normally generate. So R1, R2, you have R1 equals R2 equals F of R. Then you have only two possibilities for R1 and R2. Then either R1 is conjugate to R2, or else R1 is conjugate to R2 inverse. It's quite amazing. What you get from the fact that the two groups are the same is that you have a product of conjugates and so on, which is easy that, but you just find that two words are really conjugate, and they are conjugate either to R1 or to R2. And the advantage of using this theorem is that if you have a one-relator group, for instance, the fundamental group of a surface of genus G is exactly defined by A1, AG, BH1, BG, and precisely one relator R, which is the product of AI, BI from E equals 1 to G. Then you know what's going on when taking an automorphic. Take phi an automorphic, let's say an automorphism of phi 1 of sigma j. This corresponds basically to change R by means of to send R into another element of the free group generated by A1, AG, B1, BG, which would still have the same normal closure. Define that if you have such an automorphism, there is an induced action of phi such that when you write it phi of R, I'm putting a star here because it's not directly phi, it's phi of R. The phi R is either conjugate to R or to R inverse. And this gives you, let's say, a homomorphism of this group into Z over 2. And we said that phi respects orientation. Of phi 1 of sigma j if the first k occurs, if phi star R is conjugate to R. And this gives you an index 2 subgroup of automorphism phi 1 of sigma j. And then you could consider the following description due to Nielsen of the mapping class group of a surface in the following way. You have the mapping class group MG, and you have here outer automorphism of phi 1 of sigma j, which is defined as automorphism of phi 1 of sigma j which preserve orientation divided by the action of inner automorphism, namely by conjugacy. And this map is an isomorphism. Of course, there is a version when you have to take into account boundaries, but when you have boundaries, you should ask each remark if sigma has boundary, then you need to take automorphism of phi 1 of sigma j, which sends each conjugacy class of boundary component into equal. Okay, so this is the starting point of many research papers concerning the action of mapping class group on character varieties, because when you have a representation of phi 1 of sigma j into something, whatever it could be this something, then you have the automorphic group of phi 1 of sigma j acting on the left side of this representation variety, and from there, if you look at character varieties or you divide by the action of something on the right side, then you could get action of mapping class group. So this is the first and the only, basically the only way I know how to construct actions. As I said before, we had representations which are very difficult to obtain. Now I'm saying that there are at least actions on different spaces, and maybe this action could be used to find out representation later. Because I think we have to eat now. We already eat later. Sorry.
Yeah. More questions to the speaker. So in the Leibniz statement, you are saying the sum group given by R1, R2 is equal. It's not equal to Fn, right? In the statement, you said that R1, R2.
Yeah, sure.
Okay. More questions?
And can you explain when we take as invariant just delta invariant, we say that the manifold this invariant is for 3 spheres 1 and for other manifolds is 0. So it's not finitely generated, yes? Okay. So you can obtain it.
No, it's very delicate to obtain a meaningful representation. What you get in general, if you take a random invariant, is something infinite dimensional, and you could describe it.
And there are no conditions on finite.
Let's thank speaker once again. Just a small announce. Well, I hope everyone has all this reimbursement stuff. Just one remark. Even your housing were already paid directly. Please, however, fill all these forms, okay? Thank you very much. And you're welcome for a lunch time.
Même si vous le bougez, oui, il faut quand même vous remplissez juste ce que